Hi, so in this video we're going to be looking at Hall's random walk hypothesis. So we are going to start with the stochastic Euler equation that we found last video, and using the stochastic Euler equation we're going to make some simplifying assumptions so that we can derive Hall's hypothesis. So our first simplifying assumption is one that we've used before. It's that the discount rate multiplied by the interest rate is equal to 1. So our consumers in their utility functions are discounting at the interest rate, and this simplifies things a lot because we can effectively get rid of our discount rate and the market and preferences line up in terms of discounting. And we also make an assumption about the utility function of our consumers in the model. So we assume that the utility function takes a specific form, which is that utility, which depends on consumption in time t, is quadratic. So we have some constant multiplied by consumption in time t minus another constant multiplied by the square of consumption in time t, and we call this quadratic utility because we have a quadratic term in there, ct squared. So now that we have these conditions, we can substitute them and use them in our stochastic Euler equation to get a result which is what we know as Hall's random walk hypothesis. So for starters, we notice that this term in the Euler equation, beta 1 plus r, we can kind of just get rid of it because it now equals 1. So we now have that the derivative of consumption of utility and consumption of time t is equal to the expectation conditional on time t information of marginal utility of consumption in time t plus 1. Let's really quickly write that out. So it's equal to expected value of marginal utility of consumption in time t plus 1. So now we've used our first simplifying assumption, but the second simplifying assumption is about our utility functions, and we no longer need to use just this general form of the utility functions here. We can actually utilize this quadratic representation. So let's first find this left-hand side. Luckily, the equation I've written out here is already in time in terms of consumption in period t, so all we need to do is differentiate this with respect to consumption in period t, which very simply is consumption in t minus 2b consumption in t. Whoops, I have done that wrong actually. That is a slight mistake. It's not consumption in t, it is actually a there, because we differentiate the ct. So then we can plug that into the left-hand side of the equation, and then to get the right-hand side of this equation, the expected value, it's very similar. We're just taking this utility representation will be in time t plus 1, and we're taking expectations of it with respect to our information in time t. So I won't go through every line of working here, but as it is very similar to what we've done on the previous line, we're just now taking expectations. So again, the ct plus 1 term we'd have there would cancel out and we would get an a, and again we'd have minus 2b there, but we would have expectations of this final term, which is consumption in time t plus 1. So very, very similar to above, but we just have expectations and we're in a different time period, and we can now substitute that into the equation there. So let's do that. So we effectively set these two terms equal to each other. We have a minus 2b consumption in t is equal to a minus 2b expectation given information in time t of consumption in time t plus 1. We'll notice that we can just subtract a from both sides, and then we can multiply both sides by minus 2b. So these terms all cancel out, and we get a very neat result that the expected value of consumption in period t plus 1 given information in period t is equal to our consumption in time period t. So if our expectation of consumption in the next period is just going to be our consumption in the current period. And what does this mean? This means that consumption follows a random walk. So the best estimate of tomorrow's consumption is our consumption today. What exactly do we mean by a random walk? Is that we do have some random. There is some randomness in our consumption from one period to the next. We are uncertain about it, but our best estimate is the current period that we have. So if we were to look, say we would have consumption over time, and again I've done that wrong. We should have time on the x-axis and consumption in period t on the y-axis, and let's say we have some initial time where we have consumption there, and in each time period we'll move up and down from this consumption by some random amount. Let's say we move up to this point, and then for the next period our best estimate is our consumption at this time, and it might go up, it might go down, and then again our best estimate for the next period will be this new level of consumption, and we'll move from this. Sometimes it might stay the same, we'll have no random change, but that means we follow a random walk. There's no reversion to the mean. It's not like we're moving always to the x-axis here, or we're not moving to some value. As we go off into infinity, this is just going to take a random walk based on just random changes from each value from each time period onto the next, and all we can do is predict that our future value is going to be our current value. This also means that individuals smooth their consumption over time, so we should have changes in consumption that are completely unpredictable to us, and the only thing that's going to affect changes in consumption is unexpected policy changes. So if nothing changes, we expect that our consumption stays the same in each period, and that's why we're maximizing due to uncertainty. And if anything we didn't know about, anything that's unexpected, that will change our future consumption, and that's our random change from period to period, and that's our random walk. So as a little extension to this, we can go back to the permanent income hypothesis that we discussed in a previous video, and we derived an equation where we found consumption at time t in terms of our income and our present value income plus some initial value of assets. But now that we have uncertainty that we can add to the model, we can just alter this equation such that we have some level of expectations operator in front of it for time t. So if you don't remember this equation, check out that video. I will not derive it all again, but we derived this equation, which said that consumption in time t depends on the interest rate and our income in the future and our initial value of assets. To get a bit of intuition, we're going to set the value of initial assets equal to 0, so that our consumption only depends on our present value of income, so we'll get rid of that. And now we can write the above equation out again, just without this term, but this infinite sum here is just simply the present value of income. It's the discounted value of future expected levels of income, so it's what we presently value our future income as, so our consumption is just a function of that, or the expected level of that. So what does Hall's random walk hypothesis tell us? It tells us that when we assume quadratic utility, people will make decisions as if the random variables that they have in their uncertain model were equal to their conditional mean. So, for example, this income or present value income it is uncertain, but we're going to consume in period t as if it was equal to its mean, the expected level of income in future periods. So any volatility or any uncertainty in these future values of income, they don't matter for our current choices. We're just going to assume that things are close to their mean. So it doesn't matter, let's again say do time and income over time. It doesn't matter if our future income is like this and it's just all perfectly constant at some level y bar, or if our future income, if we use blue for this, looks like this and it's very volatile but it still has the same mean. Our current consumption is still going to be exactly the same, whether we think things are just going to be very constant in the future or we're going to have lots of ups and downs in our income. It doesn't matter for what we currently choose of consumption in period t, and this idea is known as certainty equivalence. So we just take future values as if they are equal to their mean, certainty equivalence. This does depend on some assumptions, and I won't discuss the validity of quadratic utility assumption, but there's a lot of literature about it because Hall's random walk hypothesis is quite a key result. But we make some strict assumptions about how consumers discount and their utility functions. So this won't necessarily hold in reality. We do tend to care about volatility in our future income, but this is what Hall's random walk hypothesis has to say. So that's it for this video. Make sure to check out the playlist for future videos. The next one will be on liquidity constrained consumers. Subscribe for future videos and do please drop a like if this was at all useful.